Okay, hi everybody. So this is a really good question because it really gets to the experimental design type question that we see on the AP test. So there's going to be one question on here where it's asking us to design an experiment, analyze the pretend data that we get, and then kind of examine the how good the experiment is, how little experimental error is there enough data here to actually collect stuff. So this is a good question because it gets to one of those. I think the situation itself is a little bit confusing, just because they go into a little bit of detail about how this force sensor is used. But pretty much we know, hey, we know that the magnetic force is equal to Q V cross B. So what they're saying is there's a magnetic field that's created by this wire. We are moving this charged particle throughout there, so it has a V and a Q that is perpendicular to the magnetic field, which means that there's going to be this force F in that direction. So they go into a little bit of detail about that, which I think makes it a little bit confusing. But other than that, we're good to go. We can design an experiment to figure out this magnetic permeability, this mu naught. So students perform an experiment to collect data that can be used to estimate the vacuum permeability mu naught from the slope of a graph. So we want to do something so we can graph some data, and our slope is equal to mu naught. So that's a big idea. As shown in the top view above left, a long horizontal wire carries current I towards the top of a page. On the table are tracks at different perpendicular distances d from the wire. A cart containing a force sensor Fs can move along each track with speed v. The force sensor is attached to a small object with charge positive q and measures the force F exerted on the charged object by the magnetic field from the current carrying wire as shown above right. Assume the effect of Earth's magnetic field is negligible. So derive an equation relating mu naught to the measurable quantities in the experiment. Express your answers in terms of I, D, V, Q, and F, and physical constants as appropriate. So with this first one, they're kind of priming us to think about, okay, what can we graph? What can we actually be using? So when I do this, I see this and I say, well, I have a current carrying wire, and I care about the magnetic field in that current carrying wire. So we can think back to our equations and recall that we do have this one equation before we left for break, or not really break, whatever you want to call it. We have this one equation that says, hey, this is the equation for the magnetic field in a current carrying wire. This B equals mu naught I over 2 pi times R. And this is a good idea. This is a good thing to be thinking about. Even if you forgot about this, I would just kind of scour this equation sheet for this mu naught. We know that we want mu naught in our equation, and I'm pretty sure that's the only equation on this sheet that actually has mu naught on it. So that's going to be a good place to start. Say, hey, I remember this equation. It's the magnetic field for a current carrying wire, and it's got that quantity that I need in it. So I'm going to start off with that and say B equals mu naught I over 2 pi and then times R. In this case, though, R, well, before R was just the distance from that current carrying wire. In this case, they're calling it D, and we're not allowed to use R, but we are allowed to use D. So I'm going to replace this R with D. Okay, so now I'm looking at this, and I can solve this from mu naught if I wanted to. But if I'm thinking about this, I'm not allowed to use B. So I have to do something. Let's see, I'm allowed to use I, 2, and pi are fine, and then D is fine. But I'm not allowed to use B. So I have to think about what can I do to get rid of this B. And if I'm seeing this, oh, well, I can use V, Q, and I'm measuring the F. Do I have an equation that has F, V, Q, and B in it? And I can think, oh, yeah, I do. I have this equation that says the magnetic force is equal to QV times that B, the cross product. So if I wanted to, and then we already know the directions, so I'm just going to rewrite it. And sorry, instead of lowercase q, I'm going to use uppercase Q. So say this force is equal to QV times B. And then I would want to get rid of B, so I can do that by doing a substitution. So I'm going to solve this equation for B. B equals F over Q times V. And I can sub that into my equation for B up there. So I can say F over QV is equal to mu naught I over 2 pi d. And if I want to go a little bit further with it, I could solve this for mu naught. I don't think the answer key needs you to do that, but we're going to be a little bit extra. And now we have an equation for mu naught in terms of what we are allowed to have. And now what we want is design a procedure that students could use to collect the data needed to create the graph to estimate mu naught, including measurements to be taken and any steps to reduce experimental uncertainty. So when I'm looking at this, I'm thinking about what are my independent variables, what could I change, and what's going to depend on that change. So if I'm thinking about what I'm actually measuring, usually what we're going to do is you'll set your independent variables. So those will be things that you set. These are things that you choose and change. But your dependent variables, those are really the things that you're really measuring in your experiment. You want to measure your dependent variables. You want to figure out how did your independent variable, or how did your dependent variable depend on your independent variable. So really the thing that we're allowed to measure in this experiment is pretty much just force. So really force is going to be your dependent variable because it says we have this force sensor that's allowing us to measure the force. Everything else, we can't really measure it too well. So we're going to say we are able to measure this force. Sure, other things we can measure, but those are kind of better independent variables. So there's things that we can set. We can't really set how much force we're going to have, right? That would be kind of tricky if we came in here and we said, okay, let's do stuff so we have 5 newtons, and then like trying to move it at the exact right speed so that it reads out 5 newtons. That would be a little bit harder to make that an independent variable. So we'll say that our force is our dependent variable because it's easy to set and it's easy to measure. Or sorry, easy to, not hard to set, difficult to set, and easy to measure. So then we just need to choose for our experiment an independent variable. And when we're setting up an experiment, we just want one independent variable, and it's going to be something that we can change. And then the rest are just going to be control variables. So we're looking at our equation for mu naught. We said that f is going to be our independent variable. 2 and pi we can't change. Q is just going to be the charge of our particle, so we can't change that. Excuse me. So really, if we wanted to, we could have 3 different experiments. We're only going to need to do one. Excuse me, sorry. But we could set up an experiment where we change D, where we change V, or where we change I. So we have power to control all of those things. What I'm going to do, what pops into my head right away, is just kind of based on the drawing. It looks like there's these nice segmented lines over here so that we can change D. When I'm thinking about this immediately, I'm going to set up an equation an experiment where I have D, the distance, as my independent variable. But you could really do it any way. You could have V be your dependent variable. It would just be a little bit harder to keep that constant and like measure it. And I, you could also have as your independent variable. You could say, oh, I'm going to change the voltage, and then in this power source, it's applying the current, and if I up this, then my current's going to increase, and you could calculate that. But that takes a little bit more calculation, so I'm just going to say, in my case, I want to change D. But again, you can do it any way that you want. You could change the velocity, or you could change the current. But again, I'm just going to choose the changing the D way. But either way is valid. All right, so the students are, oh, I need to actually make an experiment. All right, so I'm going to type it out instead of writing it. Okay. So I'm going to come over here, describe a procedure the students could use to collect the data. Okay. So let's start writing and then try not to make it more complicated than it needs to be. So what we're going to say is turn on the current in the, or turn on, here, let me remember it. Turn on the power supply to provide current to the current carrying wire. Check the current with an ammeter to ensure that it is constant throughout the experiment, because again, the current is going to be one of the things that's constant. And then we'll say, obtain a meter stick and measure the distance the cart is from the current carrying wire, because D is really what we're going to change. Record your value of distance, and we'll say push the cart so that it travels at a constant velocity parallel to the current carrying wire. Then we're not actually running this experiment, so we can be a little bit extra with it. We could say maybe set up a motion detector to ensure that the cart is moving at a constant velocity. So we're not running it. This is a plausible thing that we could do. So yeah, we're not running it. It's something we could do. In real life, that would be kind of a pain. But because this is just kind of a thought experiment, we want to cut down on experimental error as much as possible. So that is one way that we could do it. We're saying, hey, we need to make sure that V is controlled. So yeah, we can use that motion detector to graph velocity data and make sure that it is constant. And then we can say repeat for different distances. Or maybe we'll be a little bit more specific. Move the cart to another distance away from the current carrying wire and repeat steps 2 through 3. And then we'll say something about run 5 trials. So that's going to be one step that we can say, hey, this is decreasing our experimental error. So we can just say, again, we're not actually running it, so we can just lie and say, oh, run 5 trials. So run 5 trials to cut down on experimental error. Are decreasing. And honestly, if you wanted to, you could say, hey, we can move it along at this distance. We can do that a couple times to make sure that our force is fine. Or maybe, yeah, maybe I will say that. So set up repeat at the same distance 5 times to cut down on experimental error. Run 5 trials at different distances. Great, so that's really all I have to say for this. We've set up an experiment where we're making sure that our constants are constant and that we are changing our independent variable. And then maybe something about, set up a motion detector. And then I'll say something about actually note the value of the force given by the force sensor. So that way we are, so note and record. So that way we have a value for this force. All right, and then repeat, and yeah, we are good to go. Now it's going to be steps 2 through 4 actually. So now we have an experiment, and yeah. So then the students are to create a linear graph from the experimental data that can be used to estimate the value of mu naught. So yeah, what we're going to set up is a linear graph, and then our slope is going to have to be our value of mu naught, or the mu naught is going to have to be included into the slope. So what we have up here, what we said earlier, was we have this equation for mu naught that says mu naught equals 2 pi f times d over q vi. So we know that this is going to be linear, so all we have to do is set this up so that it's going to be linear. And we are doing, we want to know what's on the horizontal axis and what's on the vertical axis. So when we run an experiment, usually what we're going to do is put our independent variable on our horizontal axis, and then our dependent variable will pop up on our vertical axis. So let's do that. We said d is our independent variable, and f is our dependent variable. So yeah, let's set that up. So we'll move a few things around. Usually we have, right, a y equals mx plus b form. In this case, we won't have any y-intercepts. But so we'll say y equals mx. So let's get our y on one side. So I can say F equals, I can do this, I just don't know how much I want. Let's see, mu naught over 2 pi times QV QVI, and then times 1 over D. Yep, so that's good to go. So now we have kind of 1 over D is our x-axis variable, and then F is on our y-axis. So when it asks us what we want to graph, I'm going to put on the horizontal axis 1 over D, and on the vertical axis, we're going to put F. So then our slope is going to equal mu naught Q V I over 2 pi is going to equal our slope. So then describe a method for using the graph to estimate mu naught. So what we can do is, well, this is going to equal our slope, so we can say something about calculate the slope. And then theoretically from our lab, we know Q, we know V, we know I, we know 2, and we know pi. So we can say divide the value of slope by our known quantities, Q, V, I, divided by 2 pi. So if we divide our value of slope by this, we will pop out with just mu naught. So then we say another group of students performs a similar experiment, but instead of magnetic field from a wire, there's a magnetic field with a uniform magnitude perpendicular to the table. Could the procedure described in part B still be used with the modified experimental setup? For our case, the answer is no, because we set up an experiment where B is equal to mu naught I over 2 pi R. So we set up something where our magnetic field is changing with distance. If we have a uniform magnetic field, we no longer have a magnetic field that's changing with distance. It would be the same at all of these locations of D, so we couldn't do that, right? Because this would be uniform, meaning that it's the same all over this table. So before, the magnetic field is changing, like it's going to be stronger over here, and then eventually it's going to be weaker. That's not a great way of drawing that, but whatever. So then it's going to get weaker as we move further away with R, but if it's uniform, then we lose this dependence to R, and that's really, or in our case, D. We lose this dependence to D, and that was what our whole experiment was based around. So we can say no, because now the magnetic field won't change with D, because it's uniform. So that is no good. We can't do that anymore. And it says if no indicate what changes would need to be made to the procedure, we'd have to redo everything. So redo the procedure. This one can't be saved. Can't be salvaged. Because we lose the dependence that our whole entire equation was based on. If you had chosen to go through the route where you change I or change F, or sorry, not change F, change V, then you could still do it. Or sorry, not with I, because right then you're getting rid of the current, so that would automatically not be good. But if you chose to change V, then you could still do your experiment and you'd be fine, because the magnetic field you were basing everything on QVB equals F. So if you change the V, you'll still see this, or sorry, if you change the B, you'll see a change in V. So in our case, we can't even change it, we can't even salvage it, we are done with that. But yeah, so that was the experimental one. And that's what a lot of these experimental design ones are going to look like, where you kind of design an experiment, analyze that data. Hopefully that was okay. And if you have any questions, I'll be available during the office hours. Okay.